From the graceful arc of a thrown ball, we can observe the beauty of physics in action. The ball's path is determined by the forces acting upon it, including gravity and the initial force applied by the thrower, to the complex movements of planets in our solar system which are governed by the gravitational pull of the sun and the inertia of the planets themselves. These celestial bodies follow precise paths, showcasing the harmony of force and motion on a grand scale. Force and motion are fundamental concepts that shape our universe. They are the invisible hands that guide the movement of everything from the smallest particles to the largest galaxies. When a car accelerates, it's the engine's force overcoming inertia. When a rocket launches, it's the thrust overcoming gravity. Understanding these principles allows us to explain why objects move the way they do and predict their future behavior. For instance, a pendulum swings back and forth due to the force of gravity and the tension in the string, while a cyclist moves forward by applying force to the pedals. At the heart of this understanding lie Newton's laws of motion, three elegant principles that revolutionized our comprehension of the physical world. These laws explain how forces interact with objects to produce motion, and they form the foundation of classical mechanics. In this exploration, we'll delve into the world of forces, motion, and the groundbreaking laws that govern them. We'll look at real-world examples, from athletes in motion to the tricks performed by skateboarders, to see these principles in action. We'll break down these concepts into digestible pieces, using relatable examples to illustrate their relevance in our everyday lives. Whether it's the swing of a playground or the arc of a basketball shot, these principles are at play all around us. Join me as we unravel the secrets of Newton's laws and gain a deeper appreciation for the intricate workings of our universe. Through this journey, we will not only understand the science, but also see the beauty and elegance in the way our world operates. Imagine a book resting peacefully on a table. It sits there, unmoving, undisturbed, and seemingly content in its state of rest. This is a perfect example of an object obeying the law of inertia. It remains motionless until an external force, like a gentle push from your hand, compels it to move. The moment you apply that force, the book slides across the table, breaking its state of rest. This simple observation forms the basis of Newton's first law of motion, often referred to as the law of inertia. Newton's first law tells us that objects have a natural tendency to keep doing what they're already doing. This law states that an object at rest will stay at rest, and an object in motion will continue moving at the same speed and in the same direction unless acted upon by an unbalanced force. For instance, a ball rolling on a flat surface will keep rolling until friction or another force stops it. Inertia, in essence, is the tendency of an object to resist changes to its state of motion. This resistance is why it's harder to push a heavy rock than a light one. A heavier object, like a bowling ball, has more inertia than a lighter object, like a tennis ball. This is because the mass of the object directly affects its inertia. This means that it takes more force to get the bowling ball moving or to stop it once it's in motion. Conversely, a tennis ball, being lighter, requires much less force to change its state of motion. Understanding inertia helps us comprehend why different objects behave the way they do when forces are applied to them. Picture yourself on a bus that suddenly slams on its brakes. Your body, initially traveling at the same speed as the bus, is thrown forward. This is a classic example of inertia in action. Your body wants to continue moving forward at the same speed, even though the bus has stopped. The unbalanced force that stops you from continuing your forward trajectory is provided by the seatbelt, preventing you from being thrown into the seat in front. This example highlights the importance of seatbelts in vehicles. In the event of sudden braking or a collision, seatbelts provide the necessary unbalanced force to counteract your body's inertia, keeping you relatively safe and secure. Newton's second law of motion delves deeper into the relationship between force, mass, and acceleration. It states that the acceleration of an object is directly proportional to the force applied to it, and inversely proportional to its mass. In simpler terms, a larger force produces a larger acceleration, and a heavier object requires a larger force to achieve the same acceleration as a lighter object. Mathematically, Newton's second law is expressed as F equals sine ma, where F represents force, m represents mass, and a represents acceleration. This fundamental equation allows us to calculate the force required to produce a specific acceleration for an object of a given mass. Section 5, Demonstrating Newton's Second Law, a Practical Application. Imagine pushing a shopping cart at the supermarket. You walk down the aisle, selecting items and placing them into the cart. Initially, the cart is at rest. It doesn't move until you decide to push it. This is a perfect example of an object remaining in its state of rest until acted upon by an external force. When you apply a force to the cart by pushing it, it begins to accelerate. The harder you push, the faster it moves. This is Newton's second law in action, which states that force equals mass times acceleration, F equals sine ma. The greater the force you apply, the faster the cart will accelerate. This means that if you push the cart gently, it will move slowly. But if you push it with more force, it will speed up quickly. Similarly, if you have two shopping carts, one full of groceries and one empty, you will notice a significant difference in how they respond to your push. It will require more force to accelerate the full cart at the same rate as the empty cart due to its larger mass. The full cart is heavier, and thus, according to Newton's second law, it needs more force to achieve the same acceleration. This everyday scenario exemplifies how Newton's second law connects force, mass, and acceleration. The relationship is clear. More mass means more force is needed to accelerate. The force you apply while pushing, the mass of the cart and its contents, and the resulting acceleration are all intertwined according to this fundamental principle. Next time you're at the supermarket, remember that you're not just shopping, you're also experiencing the laws of physics in action. Section 6, Newton's third law, action and reaction. Every force has an equal and opposite partner. Newton's third law of motion introduces the concept of action and reaction pairs. It states that for every action, there is an equal and opposite reaction. In other words, whenever one object exerts a force on a second object, the second object exerts an equal and opposite force back on the first object. These forces always occur in pairs and act on different objects. It's important to note that while the forces are equal in magnitude and opposite in direction, they do not cancel each other out because they act on different objects. Section 7, a familiar example of Newton's third law, jumping up. A simple jump provides a relatable illustration of Newton's third law. When you jump, you exert a downward force on the ground, action. Simultaneously, the ground exerts an equal and opposite upward force on your feet, reaction. This upward force propels you into the air. The greater the downward force you apply, the greater the upward force from the ground and the higher you jump. This interplay of action and reaction forces is a fundamental principle governing motion. Section 8, the enduring legacy of Newton's laws, the foundation of classical mechanics. Newton's laws of motion form the bedrock of classical mechanics, a branch of physics that describes the motion of macroscopic objects. These laws have proven remarkably accurate in predicting the motion of objects ranging from projectiles to planets. They are essential tools for engineers designing bridges, airplanes, and countless other structures and vehicles. Moreover, Newton's laws laid the groundwork for subsequent scientific advancements. They paved the path for the development of more comprehensive theories, such as Einstein's theory of relativity, which refines our understanding of gravity and motion at extremely high speeds and in strong gravitational fields. Section 9 Conclusion, the universality of Newton's laws. From the mundane act of walking to the intricate dance of celestial bodies, Newton's laws of motion provide a powerful framework for comprehending the universe around us. These elegant principles continue to shape our understanding of the physical world, serving as a testament to the enduring power of scientific inquiry and the profound impact of Isaac Newton's legacy. As we delve deeper into the cosmos and explore the mysteries of the universe, Newton's laws remain an indispensable guide, illuminating the fundamental principles that govern the motion of objects both large and small.